When an iOS app fetches a massive JSON payload from a sender, developers frequently need to cache that data locally for offline functionality. Look at this Swift code. It takes a large file, converts it to a string, and dumps it into user definitions using a simple key-value implementation. Under the pressure of strict sprint deadlines, engineers default to this exact pattern. Because it requires zero configuration and avoids the overhead of setting up a dedicated database. But hijacking a simple configuration API to store megabytes of raw data breaks iOS memory management and cripples the device's I/O efficiency. Prioritizing this API's convenience over hardware constraints guarantees degraded app launches, severe thread blocking, and eventual data corruption. This diagram shows user definitions on disk, a single isolated .plist file. It is not a structured query system for fetching rows, but a rigid, flat list. Apple architected this strictly to hold lightweight state markers, like simple Boolean flags, basic integers, and short strings. Injecting a massive JSON payload into this container forces a severe mismatch between the data's volume and the file's structural capacity. By placing monolithic data into a flat configuration file, the OS is forced to execute highly inefficient read operations just to check if a user wants dark mode enabled. This demonstrates eager loading. The flat .plist file moves continuously from the physical hard drive into active RAM. The OS executes this synchronously at startup, loading the entire property list before the app becomes accessible. Inflating this with massive JSON linearly extends CPU disk reads. For the user, this extended read time manifests as a prolonged splash screen, or a noticeable delay before the first frame of the UI renders. Look at this system RAM gauge. Once the file lands in memory, the needle spikes to high capacity, permanently locked by the cached JSON payload. Caching this full file unnecessarily restricts system resources needed for rendering views or background processes. The eager load mechanism turns a large cached file into a dual threat, an immediate startup bottleneck and a permanent liability for an out-of-memory termination by the operating system. The architectural penalty scales further when the application attempts to modify data within that loaded file. A single Boolean changing from 0 to 1 immediately forces the entire file to be serialized and rewritten. User data files cannot execute partial updates, unlike relational databases that perform granular modifications. Repeatedly serializing multi-megabyte strings generates severe CPU strain. You end up punishing the processor every single time an unrelated, lightweight setting, like a volume slider, is toggled. Overloading user data turns minor state changes into heavyweight data processing events, draining device battery and wasting CPU cycles. Executing these massive serialization operations also introduces immediate concurrency risks. This flowchart illustrates a heavy I/O write block, intersecting and freezing the continuous execution path of the main thread. Frequent writes to oversized property lists are not thread-safe. When this blocks the main thread, UI responsiveness halts completely. The user experiences this exact processor collision in real time, as frustrating scrolling stutters, sudden dropped frames, or complete unrecoverable application freezes. Beyond UI stalling, extending the duration of disk write operations introduces a physical risk to the application's storage architecture. This progress bar represents a massive serialized write. Because larger writes take longer, the probability of failing midway increases, fracturing the .plist file. This incomplete write yields a corrupted file, causing the app to lose all stored user settings and critical authentication flags. Treating this configuration API as a data dump is a direct threat to app stability and user data integrity. Resolving this bottleneck requires routing different data types to the correct storage layers. This diagram provides a clean architectural matrix for iOS persistence, mapping data size against data complexity. Large, unstructured data like JSON payloads, offline media, and raw files belong exclusively in the file system, specifically the documents or caches directories. Complex, highly relational, and queryable data routes directly to core data or SQLite. Sensitive information, such as authentication credentials, must be secured in the keychain. Ephemeral data that requires fast temporary access but can be safely purged under memory pressure belongs in NS cache. That leaves user data's isolated in its exact quadrant, strictly reserved for lightweight user preferences and simple Boolean flags. The engineering rule of thumb is straightforward. If the data is large, complex, or frequently updated, UserDefaults is objectively the wrong tool. Looking back at that initial Swift code snippet, the surface-level convenience of a two-line implementation masks systemic architectural damage to the application. Senior iOS engineering requires designing around system constraints rather than fighting them for the sake of development speed. Caching large data in property list files guarantees slower app launches. It enforces permanent memory bloat and causes main thread stuttering during routine operations. Audit your codebases, identify any API caching logic relying on this mechanism, and refactor it into the file system or a dedicated database. True application scale is achieved by respecting the exact boundaries of every persistence tool in the iOS ecosystem. That discipline ensures your apps remain fast, stable, and responsive.